Hello, back here for the second part of the proportion inference unit. The first part was about the one proportion pieces, which was a one proportion z interval, which is essentially um, asking some random sample or getting some random sample what percent of that sample like something was going to vote for somebody, something of that nature, and then estimating with an interval what proportion of the population would vote for that candidate or the like. uh, the one proportion test, which was hypothesizing that there was a certain proportion that it was going to be for the population, and then testing that proportion. And then we did a little bit on being able to use P star, which is if you have a confidence level and a margin of error, to be able to solve back for n, so you know how many people you need to sample in order to achieve a certain confidence and a certain margin of error. This one is about two proportions, and so now we're talking about two independent groups, whether it be male and female, or 12th graders and 11th graders, or Minnetonka versus Edina, or something like that. Um, and then we're going to look for the difference in proportions or test the difference in proportions. Let's jump into it. So there's 4 steps to creating an interval and 4 steps to creating a test, similar to the one proportion piece. The interval, you could say 3 or 4 steps, and we'll get into that more. But knowing those steps is what's going to be important here. So again, the change from the 2 sample is we now collect 2 p hats, okay, from independent populations. Okay, sorry, they get cut off again here. Then we'll either estimate an interval or we'll test to see if there is a difference in the population proportions for the 2 groups by just, again, using a sample from each group. So as an example, okay, so part 1, we talked about the Bachelor, Bachelorette, and percent of students who watch that in Minnetonka High School. And we took a random sample of Minnetonka High School students, and then we estimated what proportion of students watched The Bachelor, or to determine if it was different than what we thought with a hypothesis test. So now we're going to shake it up a little bit, and rather than have Minnetonka High School students as one big group, we're going to look at independent samples of male and females and estimate the difference between the percent of each gender who have seen an episode. Okay, so there's your 2 proportion z interval. Difference in proportion right here. We use the word percent in this example, but either way, it's the same here between percent and proportion. So to do so, assume 34 out of the 60 females that have randomly been sampled have seen an episode. So what we would have there then is p hat sub female equals 34 out of 60, and 34 out of 60 is approximately 0.57. Okay, so that's the 34 out of 60 there. Now on the male side, we have 19 out of 60 on the male side that have seen at least one episode of The Bachelor or The Bachelorette, and that is about 32%. So clearly there's a difference of about 25% here. It seems pretty drastic, but again, we are only talking to 60 out of about 1,600 females in our building, and we're only talking to 60 out of about 1,600 males in our building. So in other words, is this difference of 25% big enough to say, even though we're only talking to 60, it's a big enough difference to know that if we were talking to everybody, there would still be a difference? Or is it not a big enough difference? And that's what we're going to find out here with the confidence interval. So the first step of the interval is, again, what are we trying to estimate here in terms of difference of proportion? So when we look at this here, we are estimating the difference in proportion of females versus males at MHS who have seen at least one episode of The Bachelor or Bachelorette. Now I'm also going to denote here that I'm going to do P sub females minus P sub males. So again, If you do not write this down thoroughly, it's okay, but that just means you have to include more context later. But you do need to tell the reader this: who minus whom. And so we can have that clear up front, so when the data follows, the reader knows who went first and who went second for clarity as we move forward. The second step here, similar to the one sample, is about testing for the random samples and for the large enough samples. So as we get into this, and then there's a third condition that didn't show up here, I'll get on to the next slide. So 2 SRSs is the first condition. So did we have 2 SRSs? And again, question states, quote, a random sample of 60 females and a random sample of 60 males. Okay, and we'll talk about a little more here, how you can combine that with the third condition here in a moment. But the second condition is the large enough sample. Okay, so to check large enough sample. Now, if you recall last time, it was in the first part of this, it was n times p needs to be 10 or more, and for an interval, it was n times p hat, or 1 minus p hat need to be 10 or more. That's for a 1 sample. Okay, for a 2 sample, we have to separate. We've got 2 sets, but because we have 2 sets, it's okay if it's 5 or more. Now, if you accidentally use 10, that's fine. That's not a big error, but you can use 5 or more now. So what we'd really be doing is n sub female times p hat sub female, n sub female times 1 minus p hat sub female, n sub male times p hat sub male, and n sub male times 1 minus p hat sub male. Okay, so for us here, that would be, for the females, 60 times 0.57 and 60 times 1 minus 0.57. For the males, they also had a sample size of 60. Again, the sample sizes won't always be the same, but in this case they were. 60 times 0.32 and 60 times 1 minus 0.32. Now again, these are rounded values. So if you recall, it was 34 out of 60 females had seen it. So it's really 34 had seen it and 26 hadn't. So we could calculate that, and we'd get a decimal close to those when we rounded, but it really was 34 successes, again, quote unquote successes, for people who've seen The Bachelor, Bachelorette, and 26 fails, which is people who haven't. For the males, it was 19 who had seen it and 41 who had not. Well, all of these are greater than or equal to 5, so therefore, we have a large enough sample to ensure a roughly normal sampling distribution by the central limit theorem again. And again, the sampling distribution is a bunch of samples, in this case, of differences. So we'd basically be taking p hat sub f minus p hat sub m for every single group of 60, and we'd do that millions of times, a computer would, and graphing all of those differences in the p hats would be roughly normal. So that's what that element is there. Now, the third condition here, which I apologize, I've run out of space down below for, the third condition is that we have independent samples. In other words, the males are not affecting the females, and the females are not affecting the males. So in this case, it would be like there's not a boyfriend-girlfriend combo who happen to watch this show together, even though one of them would have never watched it alone. Okay, so that would be a lack of independence. Now, as long as they're random samples, and it's only 60 out of the 1,600 males and 1,600 females, it's probably fair. And this is, again, we wouldn't really know this unless the question states explicitly independent random sample, which I might have even said on this one, but fair to believe the 2 samples are independent. So we didn't really say anything profound there. What we're doing is we're showing the reader that we know that that's important. And whether that's the reader of an AP exam or a unit test or the reader of a journal of medicine or something of that nature, where we would need to say that we ran a test with males and females, but don't worry, they weren't overlapping. It wasn't a husband, wife, boyfriend, girlfriend. These were separate independent groups, so it was fairly done. So that's the third condition. There is that whole 10n is less than capital N that I referenced last lesson, but we aren't going to get into that here. This is already a deep enough piece. I would like to note with this that these are the exact same conditions for a 2 sample. If you recall, for a 1 sample, we had that whole n times p naught or n times p hat. Here, we'll always use this for the sample size. So you don't have to change it. So we won't redo conditions here when we talk about the test side. The confidence interval is a little uglier here, but this again is on your formula sheet largely. So what you see here is the difference in the sample proportions. That's what would have been graphed for a sampling distribution. You got the critical value or the Z star, and this is the standard error of the differences. So you'll see that there's been an AP exam multiple choice question that asked, which of these is the standard error of the differences? And so to know that that's the formula for the standard error of the differences would be important. And then again, this part over here is just highlighting that this whole thing is the margin of error. So for this particular problem, I noted that females would go first. Okay, so the female 34 out of 60 or 57% is going to go first, minus the male, which was the 19 out of 60 or 32%. We're going to go 95% confidence is what the question asked. So that's 1.96 there. And that's that Z star from the table. For us, it's probably a laminated table that you have. And then it's P hat, 1 minus P hat over the N for the females, and P hat and 1 minus P hat over the N for the males. Okay, now this is a lot to actually calculate. So what we're going to do actually is use a calculator function again. And this calculator function is stat tests. And we are now going to 2 proportion Z interval, which on mine is actually B, 2 proportion Z interval. Again, not Z test and not 2 proportion Z test. It'd be 2 proportion Z interval. And it's going to ask again for the fractions. And so the fractions here for the females, X1 is 34, N1 is 60. For the males, X2 is 19, and N2 is 60. And you just put in the fractions, so you don't put any decimals in except for the confidence level being 0.95. When you calculate that, it will give us an interval, a final interval of about 0.0780 to 0.4220. Now, what's important to note about that is keep in mind we're looking for the difference in percent of females minus males who have seen an episode of The Bachelor or The Bachelorette. This is telling us that somewhere between about 8 and 42% higher percent of females have seen an episode. So that's showing there is a significant difference. Okay, if there weren't a significant difference, this interval would have crossed the number 0. Okay, if there weren't a significant difference. Okay, but because there was, in this case, yes, it was a difference of 25%, but this interval is saying if we had the whole population, that difference could have been as low as about 8%, but it also could have been as high as about 42%. So what you're seeing here is the 25% difference is what was in the middle, which is again the 57 minus the 32 there. And so the margin of error here is about 17% each direction, but either way, the margin of error was not big enough to get to the negative numbers on the left side of this interval. So we actually have evidence that a higher percent of females have seen this show. And again, we only talked to 60 of each gender. We didn't need to talk to any more. Okay, we've got the evidence based off just our 60 of each gender, so no sense in talking to the full 1,600 to be able to say that a higher percent of females have seen The Bachelor or Bachelorette. So for an interpretation of this, we put the confidence level in again. We put our interval in, and we are saying this is now the difference in proportion, in this case, who have seen these shows. So I won't write the whole thing here, but what we would say then is we are 95% confident that our interval, and our interval again went from about 0.0780 to 0.4220, contains the difference in proportion of females minus males at MHS. Sorry, I'm writing the whole thing anyways, basically, who have seen 1+ episodes of The Bachelor or The Bachelorette. Now, you can see this gets to be a lot of writing on an actual summative assessment or an AP exam, not the spot to try and skip out on words, okay? This is a spot where you need to include everything. And what I mean by everything is just, I'll highlight a couple here. You need to include the confidence level. You need to include the interval. You need to include the terminology difference in proportions, and you need to include the context. Okay, all of those things should be included here. Now, again, the other thing is I noted again females minus males. Because I noted that originally, I wouldn't have to restate it. But if you don't write that first step, then it really should be stated here. And you just need to make sure you mention it somewhere that you're taking females minus males. Okay, now the second part here will go a little quicker. So the hypothesis, again, is the idea that we are going to say that P sub male equals P sub female. Actually, I'm going to keep it as female first. I'll start that over. Female and male. And what we're probably going to test here is that a higher proportion of females. But you know what? I'm actually going to make it this one because I want to be able to talk about a little bit with how to look at an interval and a test being compared at the end. So I'm going to do that. I'm going to test if they're different. So moving into the actual hypotheses in this particular example, our null hypothesis, again, the kind of general belief up front until we show that it's not, is that the proportion of females at Minnetonka High School who have seen an episode is equal to the proportion of males. Well, we already have evidence from the interval that females are higher. We are going to just test this as being not equal. Not equal just to show what a test, how it looks a little different when it's not equal to. Now, we would have to define what does PF represent, what does PM represent. Again, PF, and I won't write the whole thing, but proportion of females who have seen an episode. Okay, you can't just say proportion of females. You got to say what they did. Proportion of males who have seen an episode, and you roll from there. So second is, again, type and conditions, and I forgot to mention last time that with the interval, it was a 2 proportion Z interval, and now this is a 2 proportion Z test. So we'd have to mention that again. And then the conditions would be exactly the same as they were before. Okay, we'd have 2 random samples. Now we can still test the n times p hat and n times 1 minus p hat for both males and females as being 5 or more, and they should be independent of each other. Okay, so this is same as interval. Okay, as the 2 proportion Z interval. But we should mention the type, that this is now a 2 proportion Z test. Okay, so the formula for this is a little more confusing. If you use your calculator will pool the p hats. And what pooling is, and this is just a generic example, but here's 2 p hats. Pooling is actually just combining or adding the numerators and then adding the denominators. So it's kind of like an average percentage of the 2. Now, in this case, since it's 200 is the n for both of them, it actually is the average of the 2. If one of the n's is bigger than the other, then it's kind of the weighted average of the two. If it was an n of 200 and an n of 100, then the 200 n would factor in more to that pooled p hat because it has a bigger portion of the overall combined sample size. But that pooled p hat is what this p is in the denominator, so you can see kind of how this formula worked. The 32 and the 46 were in the numerator, but the 39 was in the denominator. Sometimes you'll see this as two roots here, and sometimes you'll see it all under. So the separate roots here you'd see as one root, and it'd just be a multiplication of the 1 over 200 plus 1 over 200 to go along with the 0.39. So in our, we had females first. So our Z is the females. Again, I'll just write them over here. P hat sub female was 34 out of 60, which was about 0.57. The males was 19 out of 60, which was about 0.32. And then the pooled here, or the just general p hat, or you say p hat pooled or p hat combined, would be 34 plus 19 over 60 plus 60. So we've got 34 plus 19, which is 53. 60 plus 60 is 120. And that would be approximately 0.44. So we put the females first up top because the females were listed first in the null hypothesis. So since the females were listed first and males were listed second, we keep that order here. We cannot change that order. Okay, and so the denominator then is the pooled p hat, 1 minus the pooled p hat, and then 1 over the sample sizes added to each other, but still under that product. So I used it as one root. Again, you can split the root if you would like. Now, again, from this point, I'm going to go to stat tests on my calculator, and I'm going to go to two proportion z test, which on mine is number 6. And I'm going to put into two proportion z test the 34 and 60 again. So it'd be 34, then 60, then 19, then 60, then not equal to would be the 5 things I'm going to put into here. Now the not equal to, if you were to go to draw, what you would see is the not equal to just brings the p-value to both sides. So the z here, again, this normal curve is centered at 0. That would be if pf equaled pm. They wouldn't have a difference in terms of their values. But the z here ended up being about 2.76, which means the difference, females minus males, was actually way up here. And there's part of the p-value. But since it's two-sided, we actually look at the other side too. So negative 2.76. And what we're saying there is just being 2.76 standard deviations away from each other. Had we just done greater than, it would just be this one. But since we did two-sided, a not equal to alternative, right? HA was PF does not equal PM. Because of that, that ended up being two-sided. So our p-value got doubled. And so our p-value, again, this is a p-value, which isn't to be confused with p-hats or p-naughts or anything like that. This is the p-value that says basically how likely was it that these two proportions were that different. And the likelihood of that was 0.0058. What that means is that this was 0.0029 up here, and this was 0.0029, which means there was about a 1 in 200 chance that our percentages would be this much different if they were supposed to be equal. So that's assuming the null is true. So again, p-value by definition is the chances of being, in this case, that much different or more different, assuming the null is true. And the null in this problem was that they were equal, which is the center of this curve here. So there was about a 1 in 200 chance. So in other words, we either got a really rare sample, which we didn't. We didn't take a random sample. Well, we said we did. So the third option was that we are going to reject that they are equal. That's where our final conclusion comes into play here. And it's going to jump to that. So we would say, based on our evidence, which was a p-value of about 0.0058, that was less than 0.05, we reject the null hypothesis that they were equal. So there is evidence that a higher, or excuse me, in this case we use difference, so that there is a difference in the percent of females versus males who have watched an episode of The Bachelor or Bachelorette. And you could say females most likely greater, because we knew that they ended up greater in this example, in this sample here. So, but again, the reason we use the word difference is because HA was the PF does not equal PM. Okay, so again, why do we have that evidence? Well, if there's less than a 5% chance of our result occurring, we're going to say, okay, we've got the evidence we need. We had a random sample. We've got the evidence we need to reject the original claim and to say that the alternative claim is the winner, which in this case was that they were not equal. So that's our winner. And we go on and we can say most likely that it was females that were greater from there. Now, this is exactly what the interval said. Okay, the interval, because we used an alternative that was not equal to, and because we used 95 and 5 for our confidence level and significance level, we were able to basically come up with the exact same conclusion for both of these, because our interval, if you recall, went from about 7%, let's see, what was it, 7% to 42%. Okay, so we already had the evidence that females watched at a higher rate, and then we ended up getting a p-value of about 0.0058, which was less than 0.05. So both of these check the box for basically saying we have significant evidence that females watch this show at a higher rate. We could have used one or the other. In actuality, you'll never really be asked to do both of them in full in one question. You'll be asked to use one or the other, but you may be asked a question like, and this is what I'll end with, based off of this interval, is there evidence of a significant difference? And what you would say is, since 0 in this case, because it was two sample, okay, so you were looking for a difference of something other than 0, okay, which is much different now than a one sample, or you might be looking for something different than 42% or something like that for a null hypothesis. Since 0 is not in our 95% confidence interval, and then you'd go on to say there is significant evidence of a difference. So that's interval and test being combined. Again, this is the one sample and two sample for proportions of inference, intervals, and tests between the two lessons of this unit. Thank you for listening and watching, and as always, if you have any questions, please ask.